And now we get to the chemist's unit for concentration, molarity. So of course it's going to involve the mole, and in this case it's going to be moles of solute per liter of solution. So this is the most common way that a chemist would express concentration, but again, there are other ways, as we've seen, and even times when chemists would use other methods, but in particular this is the one that we're going to focus on. If 2 moles, 2.0 moles of NaCl are dissolved in enough water to prepare 1.0 liters of solution, the resulting NaCl solution has a molarity of 2.0 molar. And that's how you say it when you read the big M. Technically, the big M should be italicized. It means molar or molarity. So big M equals moles of solute per liters of solution. In this very simple example, we have 2.0 moles of NaCl and exactly 1.0 liters of solution, and therefore we come up with a 2.0 molar NaCl solution. So again, we've looked at some other methods and we will encounter them from time to time, but now that we know molarity, that's going to be the one that's most frequently discussed in this course. And then if you come and take 142 as well, we'll focus on molarity. And actually, molarity is a lot like mass per volume percent in the sense that we typically find the mass of the solute and then convert it into moles and then add enough solvent, typically water in this course. Again, we'll talk about some non-aqueous solvents in the next course, but typically it's water here for us in the 141, and we'll just add enough of that solvent to get to the 1 liter mark and to make a 2.0 molar NaCl solution. In this example, we do have smaller and larger volumetric flasks, so we could make as little as, say, 25 milliliters or even 10 milliliters, and it's very exact, or we could make 2 or 3 liters depending on how much solution we really need. So again, it's convenient because it's nice and easy to just add up to the mark and get an exact volume rather than massing the solvent or using the other methods that we've discussed. All right, so now that you have a bit of understanding about molarity, let's see how you do on this learning check. What is the molarity of a 0.350 liter solution that contains 46 grams of KCl? So go ahead, solve this thing, stop the video here while you try to figure that out, and start us back up either when you've come up with the right answer or what you believe is the right answer, or if you're really stuck, then just start right back up and see what we would do in a case like this. All right, so here we have it. When in doubt, right, step 1 is always the same. In this case, we'll analyze the problem to see that we're given a quantity of solute of 46 grams of KCl. We are given a quantity of solution of 0.350 liters, and we want the concentration. So a best guess here, since we're asking for molarity, is to figure out the number of moles. Since we know the liters and we know the mass, we can find the molarity once we've converted mass into moles using molar mass. Okay, so in this case, if 1 mole of KCl equals 74.6 grams of KCl from the periodic table masses for 1 mole of potassium and 1 mole of chloride, we can therefore find the molar mass of potassium chloride, and then we know that we can use that conversion factor in either way with the mole of KCl in the numerator and that molar mass now in the denominator, or vice versa. And when we do this, we can find that that 46 grams of KCl actually corresponds to 0.62 moles of KCl. And now we're quite far along because it's just a trivial matter of dividing that mole value by the number of liters to get the molarity. So typically your biggest challenge is to find that molar mass and convert mass in grams into moles. All right, so moving on to step 2, we write the concentration expression. In this case, it's molarity equals moles of solute per liter of solution, and that's the form we actually need because it is the molarity we're solving for in this case. So on to step 3, substitute the solute and solution quantities into the expression and calculate the concentration expression. So in this case, the molarity big M equals 0.62 moles of KCl divided by 0.350 liters of solution, and that gives us a molarity of 1.8 molar KCl solution. So if you were able to do this on your own, wonderful. If you needed some help, you may have made a mistake along the way or weren't quite sure how to get started, well, hopefully now that's no longer true and you're feeling pretty confident and comfortable here with molarity. All right, so 8.10, the table here that summarizes these concentration expressions. So in terms of concentration units, we could have a mass percent would be gram mass, at least if it's M per M, mass per mass percent expression. It'll have the solute in grams and the solution in grams. For a volume per volume percent, we would have milliliters would be the most typical, but again, any volume amount that's the same for the solute and the solution would cancel. Finally, if we want a mass per volume percent, then typically it's grams for the mass of the solute and milliliters for the mass of the volume of the solution. And then finally, our most commonly encountered one, now that we know it, is molarity, where we have moles of solute per liter of solution. As chemists, we're nuts about that mole, and when we introduced it a couple chapters ago, now we're just not going to let it go. So that's our favorite one because it deals in the mole, and the mole obviously very useful for conversions. Once we have an expression that deals in moles, we can then therefore find moles and convert moles of A to moles of B in a balanced chemical equation and so on and so forth. So if you haven't caught on yet, chemists love that mole and will use it whenever possible. Okay, so now that we know some different concentration expressions, we can think about using concentrations as conversion factors. And of course, if we're talking about mass percent or mass per volume percent, well, that value of 100 in the denominator of any percent expression is an exact number. So it does not affect the significant figures in the problem. It's not a measured number, it's an exact number. So if we look at these different possibilities for conversion factors, if we have the table 8.11, we've got 15% mass percent of a KCl solution. Well, we could say that that's 15 grams of KCl per 100 grams of solution, or we could say 100 grams of solution per 15 grams of KCl. Again, the 100 for the grams of solution is an exact number, but the 15 for the 15 grams would be our sig fig limiter at 2 sig figs for that expression. Likewise, if we go on to the 12% volume per volume ethanol solution, well, that could be a conversion factor in either the way that we see on the left with 12 milliliters of ethanol per 100 milliliters of solution, or as we see on the right, the inverse, 100 milliliters of solution per 12 milliliters of ethanol. And again, that 100 for the solution volume is exact. The 12 milliliters for the ethanol would be our sig fig limiter. Finally, we have that 5% mass per volume glucose solution. So the way we could express that as a conversion factor is 5 grams of glucose per 100 milliliters of solution, or the inverse, 100 milliliters solution per 5 grams of glucose. And yet again, the 100 for the solution volume is an exact number, but the 5 for the grams of glucose is a sig fig limiter. Finally, the most common one now, molarity. If you haven't already noticed, we can say that it's either 6.0 molar HCl solution, or more commonly 6.0 moles HCl per 1 liter of solution. And of course, depending on the setup of the problem, we might prefer to use the 1 liter solution per 6.0 moles of HCl as a conversion factor in order to cancel units and get the desired unit for the answer. So we've got lots more in our tool belt now, and that means we can do more interesting and exciting problems together. So let's not wait too long before we try a problem. So in this learning check, you'll write 2 conversion factors for each of the following solutions, just to make sure that you're comfortable with this idea of using concentration as a conversion factor. So in number 1, you have an 8.50% mass per mass of a sodium hydroxide solution. In number 2, you have a 4.8 mass per volume percent solution of hydrochloric acid, HCl. And then finally, another sodium hydroxide solution, this time 3.4 molar. So go ahead and write the conversion factors and then their inverse for each of those examples. Stop the video here, start back up when you want to check your work. Okay, so in that first example, the 8.50% mass per mass sodium hydroxide solution, that means either 8.50 grams of NaOH per 100 grams of solution, or the inverse 100 gram solution per 8.50 grams NaOH. For number 2, we have a 4.8 mass per volume percent solution of HCl, so that could either be 4.8 grams HCl per 100 milliliters of solution, or the inverse 100 milliliters of solution per 4.8 grams of HCl. Finally, our 3.4 molar NaOH solution would be either the more typical 3.4 moles NaOH per 1 liter of solution, the definition of that molarity, or if the problem calls for it, the inverse 1 liter solution per 3.4 moles NaOH. So hopefully you're quite comfortable with these already, and that didn't take you much time at all to get it correct. Otherwise, if it is causing you some trouble, then please do try some additional examples on your own. And as always, reach out to me if you need additional help. All right, so since we've already introduced the idea of concentration as a conversion factor, let's go ahead and look at our guide, how we modify our guide to use concentration to calculate mass or volume from the concentration conversion factor. So first of all, like always, state the given and needed quantities. This is where we're going to analyze our problem. Number 2, we'll write a plan to calculate the mass or the volume, whichever the question asks for, and ultimately moles could be asked if it's a molarity type problem as well. Number 3, we'll write equalities and conversion factors, and then 4, we'll set up the problem to calculate the mass or volume using those correct forms of the conversion factors that we have written based on the equalities present. So minor modifications to our typical plan, and hopefully this guide will serve you well should you need to calculate mass or volume using concentration. All right, well, I guess you didn't have to wait too long to apply the new guide, because here's a learning check that asks you to do just that. How many grams, so we're looking for mass, of NaCl are needed to prepare 225 grams of a 10.0% mass per mass NaCl solution. So please go ahead and pause the video here, apply those steps, solve this thing, and then start us back up to see how you did. Okay, in step 1, as always, you analyze that problem to find that you're given the 225 grams of NaCl solution that you need. You're given that it's a 10.0 mass per mass percent NaCl solution, and you need to know the number of grams that were required to make that solution. Moving on to step 2, now we'll write our plan to calculate ultimately the mass in this case. So we have the grams of solution. We'll use that mass per mass percent factor to get to grams of NaCl. All right, now moving on to step 3, we can write our equalities. Because it is a 10.0% mass per mass solution, we can say that 10.0 grams of NaCl equals 100 grams of this NaCl solution. And that 100, of course, is an exact value, and the 10.0 grams is a 3 sig fig value. Okay, so then we can express it with either species in the numerator or denominator of that equality. In step number 4, when we set up the problem to calculate that mass, we'll see that we need to have the 10.0 grams of NaCl in the numerator and the 100 grams of NaCl solution in the denominator, so that we can cancel the grams of NaCl solution and ultimately find that we need 22.5 grams of NaCl in order to make that solution. So hopefully that was pretty straightforward, didn't take too much of your time and effort to figure that one out. And if so, then great, you're ready for another one. If not, well, then the best way to get there is to practice with another problem. So let's move on to a second learning check here. All right, in this case, we're looking now for volume. So how many liters of a 2.00 molar NaCl solution are needed to provide 67.3 grams of NaCl? So go ahead, stop the video here, and use the guide there now this time for volume in order to solve this learning check. Then start back up when you're done, and we'll see how you did. Okay, so here we are in step 1, analyzing the problem. This time we see we're given 67.3 grams of NaCl. We are told that it's a 2.00 molar NaCl solution, so we need to know how many liters of NaCl solution would be needed to take that mass of NaCl and make that concentration of solution. Moving on to step 2 here, we can say that starting with the grams of NaCl solution, we can, or grams of NaCl in this case, use the molar mass to get the moles of NaCl, and then the molarity to find the liters of NaCl necessary. Moving on to step 3 here, we can write our equalities and conversion factors. First of all, in this case, we do have the additional need for that molar mass of NaCl. So 1 mole of NaCl equals 58.5 grams of NaCl. So we can express that conversion factor in either way. And finally, we have our 2.00 moles of NaCl equals 1 liter of NaCl solution, and we can express that conversion factor in either way. And once we move on to step 4, we'll see exactly what way we need to set it up in order to cancel out our starting grams of NaCl and find that liters of solution at the end. All right, so finally now in step 4, we can set the problem up in a dimensional analysis scheme that will allow us to cancel units and arrive at the desired volume of NaCl solution. So in this case, we start with that 67.3 grams of NaCl. We'll multiply through by the molar mass, where we have the form 1 mole of NaCl per 58.5 grams of NaCl. So now grams of NaCl is canceled. We're in moles of NaCl. If we multiply by 1 liter of NaCl solution per 2.00 moles of NaCl, now we can cancel moles of NaCl. We're left in liters of NaCl solution, which is what the problem wanted to know. And we find that it is 0.575 liters of NaCl solution that would be needed for that a mass of NaCl if we want a 2.00 molar NaCl solution. So hopefully this one wasn't too much more difficult for you. If it was, please do try additional problems and reach out to me for some guidance. But assuming everything's going fairly well, we'll plan to meet up again for section 5 of chapter 8.